Thai. Well, that's the way we say hello in Laos. Hello children, how are you people doing? I'm Saurabh Kumar Dutt and I'm here to teach you people a little bit of mathematics. Now children, before I get started and make your maths really strong, let's take a quick tour to Laos. This fascinating place that you get to see is Quang Si Falls, Long Prabang, Laos. This is a 3-tier waterfall atop steep hillside which has a drop of 60 meters. The water cascades into turquoise blue pool which further moves downstream to Mekong River. I'm sure you'll really be fascinated by the scenery here, and do not forget to have the local sweet dish of Laos, which is khao lam bamboo rice. Also, do not forget to tell all the people of Laos that you get to meet Thak Thai. In this note children, I'll again say Thak Thai, but now it is to geometric progression, where first we'll be discussing the three terminologies that we normally get in this chapter, that is either a sequence or a progression or a series. After this, we'll be quickly looking up the concepts of a geometric progression, and then we'll get along with the sum. And I'm sure if you stay till the end of this lecture, you will have made good advance in this topic. Further, if you want more help, then obviously you should get into the app that I have, that is the Mathematics Helpline, where you will get utmost amount of help in the topics in which you really dread. So children, let's get started and let's look up what the difference between these three terminologies is. Right? The first that I said to you people is a sequence. So as it can be understood, this is something which is very basic, which is what you normally use in normal life. So when we talk about a sequence, that means there is some logic which is bringing in this group of, say, terms or names or say some numbers together. For that matter, if say we write an array or a group of prime numbers, right? Obviously, say from the start to say any long, or probably we can start from a big prime number getting to a smaller prime number. Obviously there has to be an order. Or say if we write the geometrical forms like a triangle, then we talk about a square, then we talk about a pentagon, right, and so on. Further, we can even write the names in order, right? Then all of this will form a sequence. Now, to give you a very good example of what a sequence is, I'm sure you people must have seen where your class teacher maintains the names of your attendance register. Your names are either in the first name's alphabetical order or probably the second name's alphabetical order. But whatever it is always an alphabetical order of your names. So if you write all of the names one after another, separating them with a comma, you will get a sequence. So is all of this perfectly clear? Right. So after this children, next is a progression. So when we talk about a progression, this becomes mathematical. So in a progression, there is a mathematical rule which relates all the terms which are there in the group, right? So if say we talk about an arithmetic progression, you knew that when we talk about this, every term is differentiated from the earlier term by a constant which was added to the last term, right? Similarly, when we talk about a geometric progression, or if we talk about a harmonic progression, or if we talk about a progression of any type, I'm sure now you will be able to understand that all of these elements in the group or in the array have a common rule which relates all of these. Next now children, after this, we now talk about a series, right? When we talk about a series, it is nothing much different than a progression. The only difference is, in place of keeping a comma in between any two terms of a progression, you keep a plus sign, right? So here children, we are not interested about what the sum is going to come to be, but we are interested in showing that all the terms have been added up together to give you a sum, right? So this representation of all the terms of the progression with a plus sign in between each of the two, right, is known as a series. Now children, I'll just quickly repeat all of this so that all of this is perfectly clear. I can see that Kajol is making some facial expressions which shows that she has some ambiguity. Doesn't matter, I'll just quickly repeat. So just focus. For that matter, always focus where exactly I am if you let your focus be not associated with where I am, then you will not be able to understand, right? And that is the reason why I give you a second explanation every time, so that if you miss something somewhere, you're always able to link up. Okay, children, so if say we talk about these three terms, a sequence, a progression, and a series. Sequence is the one which is most basic, because that is used in English language as well, where we know that whenever we talk about a sequence, it's an array or it's a group of some entities which are in accordance with some logic, right? So we can be having a group of names which are having this logic that they are all in alphabetical order of the first names. Similarly, we can be having some geometrical shapes, like we can be having a triangle, a quadrilateral, a pentagon, and so on. So all of this will also form a sequence. Now when we talk about progression, it becomes a sequence, but here the terms are not names or any other structures or probably anything else, but they are just numbers, right? And what relates each of these elements of the progression is a mathematical rule, right? And when that is there, then you say that the terms are that of a progression. Now children, in writing the terms of the progression, if in place of writing a comma between any two terms, if we use a plus sign, then that will be known as a series, right? So this is what these three terms are and what is their basic difference. This can obviously be asked to you in any theoretical question, or probably it can be an optional question as well, and normally children get confused in all of these three concepts. Now children, after discussing this, next now I'm going to talk about what a geometric progression is. Now as you get to see that this is a progression, so obviously the first thing that you get to understand that this is going to be mathematical, right? And when we talk about the terms, they're going to be separated by a comma. Now what is going to be the common rule which associates all of these elements? So for that matter, now if say we talk about the first element, let's say it be A, then the second element is AR, the next element is AR square, the next element is AR cube. So I'm sure everybody in this class is able to understand that there is a number or a constant R which is getting multiplied with each of the earlier terms to get to the next term, right? And this R, children, is known as the common ratio. What is it known as? It is known as the common ratio. Now children, this can very easily be shown by a formula. So here what you can do is, if say now we talk about the ratio of the second term which is going to be divided by the first term, or if we talk about the ratio of the third term which is divided by the second term, right, we will get the common ratio. Now here children, I'm sure you're able to see this, that if ever we talk about the ratio of any two consecutive terms, for that matter, if we talk about the ratio of the 19th term to the 18th term, where the term which has come later is in the numerator and the term which has come earlier is in the denominator, then this ratio is known as the common ratio. Now this is a characteristic of any of the terms which are in geometric progression, right? Now children, after we've looked up what the common ratio is, right, we obviously would like to find out any term in a geometric progression. Now when we talk about that, then we talk about the formula for the nth term, that is Tn, and that is given by a times of r raised to the power n minus 1. Now here children, as you get to see that a here is the first term, r is the common ratio, and n is the number of terms. So this is what is going to give you the nth term, right? Sometimes it is also said to be L, that is in place of Tn you can also write L, that is a representation that it is probably the last term. Now children, after this we'll talk about the sum of n terms of a geometric progression. Now a geometric progression can be said in abbreviation to be GP, so no need to tell about these two big terms, right? So you can just say GP. Okay, so children, here next now when we talk about the formula which shows the sum of n terms, there can be two variations in it. The first is when we talk about the common ratio to be one such whose modulus is greater than 1, and the other case is when the modulus is less than 1. So first children, let's consider that case where the modulus or the absolute value of r is greater than 1. So if you talk about the modulus of r to be greater than 1, right, we'll quickly be having an example. For that matter, if say we talk about the value of r to be 10, so we know that if you find out the modulus of this is going to come to be 10. Similarly, children, if we talk about here r to be 1 such where we have the value of r to be say minus 19. So if we talk about the modulus of r, then that obviously is going to become equal to 19, or in other words, we'll just be taking a positive value. So if it's negative, you're going to multiply it by minus sign, right? So this is what is absolute function, or this is the modulus function. So we've got to remember that whenever the common ratio is such that its modulus is greater than 1, then this is the formula that is going to be applicable. That is, we'll be talking about Sn to be equal to a times of r raised to the power n minus 1, which is going to be divided by r minus 1. Now, children, is the next case when we talk about the common ratio r to be 1 such whose modulus is less than 1. And if that is the case, then children, here we will have another formula which is Sn is equal to a times of 1 minus r raised to the power n divided by 1 minus r. Right? So here you got to remember that this second formula is going to be applicable when the modulus of the common ratio is less than 1. Right? Now, children, after this we have another formula which tells us about the sum of the infinite terms of a geometric progression. So when we get some such sort of a series, then obviously if the common ratio is greater than 1, like suppose if we take it to be 10, then obviously it can go for infinite terms, but we won't be able to find out the sum of that, because how long will we be able to add? And that is why we can find out the sum of the infinite terms of a geometric progression only when the modulus of the common ratio is less than 1. So as such, here when we talk about the next formula, which say is S infinity, then you got to remember here that the formula is only applicable when the modulus of the common ratio is less than 1. So S infinity, or the sum of the infinite terms, is then given by a upon 1 minus r. And here, children, you got to remember this, that the modulus of the common ratio has to be less than 1. Right? So all of these concepts, children, I'll just quickly discuss. Here we are discussing about a geometric progression. Now, if we talk about the terms which are there in a geometric progression, we know that all of these will be having some mathematical rule which will relate them all, and they'll all be separated by comma. Further, if we talk about the first term, it is say some a. The second term, it is say some AR. The third term, it is say some AR square, and so on. Obviously, this can go on for n terms. Now here, when we talk about this R, it is the common ratio. Obviously, A is the first term. Now, the common rule which relates them all is if we divide the second term by the first term, or if we divide the third term by the second term, for that matter, if we divide any later term by the just earlier term, right, that is T19 upon T18, which are just consecutive terms, then we get the common ratio. And this is something which should always remain to be constant for any two pair of terms which are in a geometric progression. Now, children, after this, we talked about finding out the nth term, or probably the last term L, for a geometric progression. And that is given by A times of R raised to the power n minus 1. Now remember here, children, when we are to find out the sum of n terms of a geometric progression, then we have two cases. The first case is when the common ratio R has its modulus to be greater than 1, and the other case is when the common ratio R has its modulus to be less than 1. When it is greater than 1, then the formula for the sum of n terms is given by A times of R raised to the power n minus 1 divided by R minus 1. And when the common ratio has its modulus to be less than 1, then the sum of n terms is given by A times of 1 minus R raised to the power n divided by 1 minus R. Now further, children, we also have the case when we find out the sum of infinite terms of a geometric progression, but that is only possible when the common ratio's modulus is less than 1, because if it's a large number like 10, it can go up to infinity, but we won't be able to add the terms, as how long will we be able to keep adding, right? So the sum of the infinite terms of a geometric progression can only be found out if the modulus of the common ratio is less than 1. Now children, these were the formulae which require to be applied. Now let's get along with the sum. So initially, after I give you the sum, I like you people to first try it out with whatever logic you can, and after that I like you people to look up the solution, and further then again you will pause and you will do the sum all on your own. And lastly, I'll give you a sum, right, which you all require to do after you look up this lecture, right, whose solutions or whose pics taken by your mobile can very easily be sent to me in my email ID, which is saurabhkumardutt@gmail.com. So that's my email ID, which you can even see at the end of my description of the YouTube channel, right? And very easily you can send a mail, which I'm sure I'm going to correct it, right? I'm going to check it, correct it, and then I'll send it back to your email, right? So let's quickly look up what the sum is after I give you people a little time for trial. Trial means trial. That is the time when you have to honestly give it a good thought, right? If you want more time, obviously you can pause the lecture and give it a bigger try and then come back and look up what the solution is. Now children, here, if we talk about the sum, we have this series, remember, as we last discussed, and that is 0.5 plus 0.55 plus 0.555, and all of that continues up to some terms, and we've got to find out the sum up to n terms of this series. So what we do is we consider this to be, say, some Sn, right? So this is an assumption. Next, what we can do is we can write what this assumption is equal to. That is, it is equal to 0.5 plus 0.55 plus 0.555, and all of that, children, continues up to n terms, right? Next, what we can do is we can talk about writing this to be such that all of these decimal numbers have their decimals shifted. As such, we will have some powers of 10 in the denominator. As such, the first one is going to become equal to 0.5, where we can shift one decimal and it will become 5 upon 10. In the next case, it will become 0.55, where we can shift two decimals and it's going to become equal to 55 divided by 100. The next one is going to be 0.555, where what will happen is when you shift three decimals, we will have 1000 in the denominator, or 3 powers of 10 multiplied together in the denominator. Now children, remember, all of this is going to continue up to n terms, especially because we are talking about the sum of n terms, so we need not write this here. Next, now children, do not simplify this, right? Remember, Kajol, do not simplify this. Whenever you find some factors in the numerator and the denominator, you just joyously reduce them. But that is always not successful. You have to do it astutely. You've got to do it only when it is going to help you. Sometimes what happens is, if you quickly reduce it, then you will have broken a pattern which is going to be made if the common factors are not cancelled off, of whose benefit we can very easily take. So as such, here children, what you can do is, here we get to see that we have 5 from the numerator which can be taken common outside, as 5 is the common factor to all the numerators. So if we take this 5 to be common outside, now we'll just be left out with 1 upon 10. The second term is going to be 11 upon 100. The third term is going to be 111 upon 1000. Right, and all of this, children, is obviously going to continue up to n terms. Now after we have this is further going to be written now in a little different way, so that we can solve this a little more and we can start seeing that this is a geometric progression. So if here, children, we divide by 9 and if we multiply by 9, then this can happen. So 9 with which this number, that is the sum of all of these terms, was divided is outside, and 9 with which all of these terms is going to be multiplied is taken inside. As such, it is multiplied to all the numerators, and thus it will give you 9 upon 10 plus 99 upon 100 plus it will be 999 upon 1000, and children, all of that is going to continue obviously up to n terms. Now next, what you can do here is, as you now see something which is happening, we have 9 upon 10, 99 upon 100, 999 upon 1000. Yes, Kajol, tell me what's happening. the numerator is just 1 less than the denominator. So we have come close to getting to a logic. So obviously here we can now write 5 upon 9, and here the numerator can be written as 10 minus 1 divided by 10, as it is just 1 less than 10. Now the next term is going to become equal to 100 minus 1 divided by 100. The next one is going to become equal to 1000 minus 1, which is going to be divided by 1000. And children, all of this obviously is going to continue up to n terms, whose sum is next going to be found out. Now here children, there is one rule that we can apply, and that is really going to help us. That is, if we talk about, say, some a plus b which is divided by c, then we can obviously write this as a upon c plus b upon c, right? So when we do this, children, here these fractions are going to be pretty much simplified. As such, you'll be able to see a lot. Let's see what will happen. This is going to become equal to 5 upon 9 times of, we will have 10 upon 10 minus 1 upon 10. Next is going to be 100 divided by 100 minus 1 upon 100. Next is going to be 1000 upon 1000, right? Minus 1 upon 1000. And obviously, children, all of this is going to continue up to n terms. Now next, children, what we can do is we get to see here that there is now some simplification that we can do so that we can get simpler things. Now 1 power of 10 from the numerator and from the denominator can be cancelled off in the first term. Now in the third term, we have 1 power of 100 can be cancelled off from the numerator and from the denominator, and similarly 1 power of 1000 can be cancelled off from the numerator and from the denominator in this 1, 2, 3, 4, 5, fifth term. Now similar is the thing which is going to happen in all of the different terms. That means all of these different terms, which were actually the first terms of the terms, they have all broken down to 1. As such, in the next step now, we can write this to be 5 upon 9, right? And here further we have 1 minus 1 upon 10. Next we have 1 minus 1 upon 100. Next we have 1 minus 1 upon 1000, right? And all of this is going to continue up to n terms. Next now, children, we get to see that this has become pretty simplified, and we can even see a geometric progression. For that matter here, next what we do is we can now write this as 5 upon 9, and we can accumulate all of these ones. As you get to see that we have 1 1 here, we have the second one here, we have the third one here. So every term has given us 1 1. So obviously the nth term would also have given us 1 1, and as such here we can say that we have n ones which are going to be added together. So as such we have 1 plus 1 plus 1, and all of that is going to happen for n terms, right? Now this is how we break up the first terms. Now if we talk about the second terms, we find that there is a minus sign which is common to all of these terms. That is, we have minus 1 upon 10 minus 1 upon 10 square or 100 minus 1 upon 10 cube or 1000. So as such here what we can do is we can take the minus sign common outside, and then within brace bracket we have 1 upon 10 plus 1 upon 10 square plus 1 upon 10 cube, and all of this is going to continue up to n terms is what we have here. Now children, after we have this, next what we can do is, if say we now talk about adding up say n ones, how can it be done? Let's do it in a simple way. Say if we want to add 3 ones, what will we get? We will get 1 plus 1 plus 1, that is 3. If we add 7 ones, then obviously it will become equal to 7 similarly. Now similarly, if we add say probably 99 ones, then that will become 99. And thus if we are to add n ones, so obviously it will become n, right? So as such here, the first term thus just becomes equal to n. And if you talk about the second term, we now can very easily see that this is a geometric progression, as the first term is 1 upon 10 and the common ratio is also 1 upon 10, which we can get by dividing the second term with the first term, which again can be got by dividing the third term with the second term. And all of this is going to happen throughout in this geometric progression, which shows that this is a progression as well as a geometric progression. Am I right? Am I right? No, I'm not, because there is a plus sign in between. So obviously this is a geometric series now, not a geometric progression. Like I told you, if the separator is a comma, then you can call it a progression. But if the separator comes out to be a plus sign, then you will say that it is a series. Remember this, okay? Sometimes I'm trying to confuse you so that I try and check whether your attention is there or not. Okay, now children, the next thing is, if we talk about now these terms which are in a geometric progression and we've got to add them, we find that the common ratios modulus, that is 1 upon 10 mod, is 1 upon 10, which is less than 1. As such, now we're going to use the second formula. Right now, to quickly remind you people about what the formula was, Sn is equal to a times of 1 minus r raised to the power n, which is going to be divided by 1 minus r. Right, so using this formula, children, we will now have this to be n minus a, which is 1 upon 10 times of 1 minus r, which is 1 upon 10, which is going to be raised to the power the number of terms, which is n, right? And it is going to be divided by 1 minus r, that is 1 minus 1 upon 10. Now children, in the next step, we just have to simplify this and then we'll get to our answer. So this comes to 5 upon 9 times of n minus, we have 1 upon 10 times of 1 minus 1 upon 10, which is raised to the power n, which you need not simplify. Let it remain to be as it is. Now the denominator requires to be simplified, where we can take an LCM, so it will become 10 minus 1 divided by 10, and then we'll close the bracket. Now for the children, in the next step, what we do is we will write this to be 5 upon 9, still staying outside, and inside we have n minus 1 upon 10. And here obviously this 10 minus 1 upon 10 is going to become equal to 9 upon 10. And as we have one fraction which is divided by another fraction, so this fraction can come to the numerator if we write the reciprocal of it, right? Because whatever comes after division sign, if you convert that to multiplication sign, then the number which is after it, you write its reciprocal. I'm sure you must have learned this in board maths. So as such, here you have 1 upon 10 into 10 upon 9, which is going to come here, where 10 and 10 will cancel each other, and inside here you have 1 minus 1 upon 10 raised to the power n, right? And that is what it is. Now children, after this we can get to our final answer, that is 5 upon 9 times of n minus 1 upon 9 is all that remains inside, and further here inside we have 1 minus 1 upon 10, which is raised to the power n. Then we close the brace bracket and we also close the simple bracket, and finally this becomes the answer. So children, now I'll just quickly discuss all of this so that if there is any doubt withstanding, all of that gets cleared. Now here's, children, we had to find out the sum of a series that was 0.5 plus 0.55 plus 0.555, and all of that was continuing up to n terms, which had to be added together. So now what we first do is, as all of these are decimal numbers, so what we do is we shift a decimal, right? And then we get the first term to be 5 upon 10. We shift 2 decimals in the second term, we get 55 upon 100. We shift 3 decimals in the third term, and thus we get 555 divided by 1000, and all of that continues up to n terms. Now remember here, children, we are not to simplify the common terms in the numerator and in the denominator. Rather, from the numerator, if we take 5, which is the common factor outside, we will get 1 upon 10 plus 11 upon 100 plus 111 upon 1000, and all of that continues up to n terms. Now next, children, if we multiply the series with 9 and divide it by 9, then outside we can write 5 upon 9, and inside 9 is taken and is multiplied to each of these terms. Now further, it becomes 9 upon 10 plus 99 upon 100 plus 999 upon 1000 plus and so on up to n terms. This is what is within the bracket. Next, children, what we do is, if we talk about this 9, it can be written as 10 minus 1. This 99 can be written as 100 minus 1, that is, the numerator gets converted to denominator minus 1 for all the different fractions. Next, now after this, what we do is we can now write this as some a plus b upon c, which can be written as a upon c plus b upon c. As such, this is going to become equal to 10 upon 10, which is 1. Similarly here, we will now have 100 upon 100, we will have 1000 upon 1000, when each of these fractions are written like 10 upon 10 minus 1 upon 10, or something like we had just discussed here, that is the numerator upon, rather the first term of the numerator upon the denominator plus the second term of the numerator divided by the denominator. Now in each of these fractions, right, we get the first terms to be 1 now. That is 1 minus 1 upon 10, 1 minus 1 upon 100, and so on. So all of these ones can now be accumulated, and as such here you will get it to be 1 plus 1 plus 1 coming up to n terms. That is because each of these terms, right, has given us 1 1, right? So obviously when we go in for n terms, there'll be n ones. Now here, children, we talked about one thing, that if say we talk about adding ones, say if you've got to add 4 ones, it's going to give us 4. If we add 11 ones, it's going to give us 11. So if we have n ones added together, it'll give us n, right? Now if we talk about changing our focus to the second terms, we find that minus sign is what you can take common out of the second terms, and when you do so, here you'll be left out with 1 upon 10 plus 1 upon 10 square, and all of that continues up to n terms. Now here, children, we get to see that this is a geometric progression where the first term is 1 upon 10 and the common ratio is also 1 upon 10, as if you divide 1 upon 100 by 1 upon 10, you will get 1 upon 10, and similarly if you divide the third term 1 upon 1000 by 1 upon 100, again here you will get 1 upon 10. So using these values and using the formula that you just learned, that is Sn is equal to a times of 1 minus r raised to the power n upon 1 minus r, that is when you have the common ratio r, its absolute value, to be less than 1. This is the formula which is used, and here in this case, as you see that the value of r is 1 upon 10 whose modulus is less than 1, and that is why we'll be using this formula to find out the sum. So here first we have n minus, now writing the sum of the geometric progression, a which is 1 upon 10, right, times of 1 minus r which is 1 upon 10 raised to the power the number of terms which is n. Now this is going to be divided by 1 minus r, that is 1 minus 1 upon 10. Now for the children here, what we can do is the numerator cannot be changed much, but if we talk about the denominator, we can take an LCM and make it 10 minus 1, that is 9 upon 10. Now in the next step, what we can do is, as this fraction is such that this is the numerator and this is the denominator, so we can write it to be the numerator into reciprocal of the denominator, that is 10 upon 9, right? Now here 10 will get cancelled, and whatever remains will become your final answer, that is 5 upon 9 times of n minus 1 upon 9 times of 1 minus 1 upon 10 raised to the power n, right? And that is all that you have in the sum. So is everybody clear about this? Sure? Really? That's good, children. Now I'm sure you people must have enjoyed this lecture. So if you have, make sure you tell how you liked it, right? And obviously there's a sign which shows that you can easily tell whether you really liked it, right? And if you disliked it, then obviously you can press the dislike button. Second thing is, I like to know that what is the new thing that you learned here. Was there something special that you got to that you learned here? Next, you can also tell what else can be those topics where we can make lectures so that you people can be helped more, right? And make sure, if you really want to be helped, then get to the app, the Mathematics Helpline, in the Play Store, and I'm sure you'll be helped much. So children, bye for now. Have a nice time, do mathematics and have fun. Bye.